You've done the from to chart. You have the relationship chart. You've calculated your scrap rates, sized your machines, and formed the manufacturing cells. Now comes the question that all of that work was building toward. Where exactly do you put everything? That's what layout planning is, and it's not intuitive. A factory with 10 departments has over 3 million possible arrangements and algorithms. That makes this traceable. Apple's and Reed's systematic procedures, Muther's SLP framework, and the pairwise exchange improvement algorithm that lets you optimize an existing layout quantitatively. This is our layout for week 13. So let's start with block layout versus detailed layout. So layout planning operates at two levels. The block layout shows the location, shape, and size of each planning department. It's the strategic level. The detailed layout shows the exact location of every machine, workbench, and storage area within each department. It's the tactical level. Our focus this week is on the quantitative methods for developing and evaluating alternative block layouts. Once the block layout is settled, detailed layout follows within each department. These are the four basic types of layouts. There's product layout, fixed product layout, product family layout, and process layout. A critical difference to flag. In fixed product layout, the fundamental principle reverses. In every other layout, materials come to the workstation. In a fixed product layout, the workstation comes to the material. Boeing assembling a 777 is the canonical example. The aircraft does not move. The tools and the workers move around the aircraft itself. So, here's some advantages. All layout procedures fall into two categories. Construction methods develop a new layout from scratch, starting with no prior layout and building one. Improvement methods start from an existing layout and seek improvements through exchanges or modifications. Three original approaches to layout planning dominate the literature. Apple's detailed 20-step procedure, Reed's 10-step systematic approach, and Muther's systematic layout planning, which is the most widely used framework in the industry today. So, Muther's systematic layout planning is built around a 10-step process, but its foundation is an activity relationship chart, the closeness in ratings between departments we covered in week 10. Two parallel analyses drive the entire SLP process. First, material flow analysis using the from to chart. This quantifies how much moves between departments. Second, activity relationship analysis using the relationship chart. This qualifies how important proximity is. These two analyses combine to produce the relationship diagram, a spatial positioning of departments that reflects both quantitative flow and qualitative relationships simultaneously. Now let's talk about the relationship diagram. The relationship diagram uses a specific visual convention to show closeness. The number of lines connecting two departments reflect their closeness ratings. Four lines for A, absolutely necessary. Three for E, especially important. Two for I, one for O. No lines for U. And a zigzag line for X, which is undesirable. These closeness values also carry numerical weights, which are shown as you can see here. The large negative weight for X is intentional. An undesirable adjacency should be actively penalize any layout that it creates. In the relationship diagram, all departments are initially shown as the same size. The goal at this stage is purely to get the spatial proximity right. Departments with the ratings that are placed immediately adjacent. Departments with X ratings are placed as far apart as possible. The result is a network diagram showing the ideal neighborhood structure for the facility. So, let's talk about the space relationship diagram. The relationship diagram treats all departments as equal in size. That is not realistic. A warehouse is not the same size as an inspection room. The space relationship diagram corrects this. Each node in the relationship diagram is resized to reflect its actual area requirement. A department requiring 1750 square feet gets a much larger block than one requiring 75. The proximity structure stays the same, only the areas change. This area-weighted diagram is then fitted into the actual available building shape. Fitting the weighted diagram into the building footprint generates alternative block layouts labeled A, B, and C, and so on. Each alternative satisfies the proximity requirements but arranges the departments differently within the available space. So, now let's talk about alternative block layouts and preferred layouts. Multiple alternative block layouts are generated from the space relationship diagram. Each one is a valid layout. It respects the proximity requirements and fits within the building. But they differ in which department end up adjacent, which end up far apart, and how aisles are configured. Based on modifying considerations, aisle requirements, building columns, safety regulations, expansion plans, and practical limitations, the alternatives are evaluated using objective functions. The preferred alternative is then identified and recommended for implementation. Now, let's talk about different algorithm approaches. SLP and the original procedures provide an excellent framework, but they do not give us the formal algorithm for evaluating specific layout alternatives. That is where layout algorithms come in. Two objective types. There's distance based, which is to minimize, and there's adjacency based, which is to maximize. Well-known algorithms, craft, block plan, logic, multiple MIP, graph based, and pairwise exchange method we cover now. So, the pairwise exchange method is an improvement algorithm. Start with an existing layout. Try every possible pair swap. Select the one with the largest cost reduction. Repeat until no improvement is possible. So, for departments of equal size, as you can see here, the material flow matrix, F from 1 to 2 is equal to 10. From 1 to 3 is equal to 15. From 1 to 4 is equal to 20, and so on. Distance matrix for a linear layout adjacent departments are one step apart. One apart are two steps. End to end are three steps. So now let's talk about pairwise exchange for iterations. After our first iteration, there's six possible exchanges from the initial layout, 1, 2, 3, and 4. We've selected the lowest layout in exchange, which is exchange 1 to 3. The steepest descent, we select the exchange 1 to 3 with total cost 95. So the new layout after iteration would be 3, 2, 1, 4. As you can see here. See how here the layouts we picked the lowest one for our total cost, and after we've done that, we made a new layout. Now we go on to the second iteration. We choose exchange 2 to 3 because it has the lowest total cost. Iteration 3 starts from layout 2314 with total cost 90. Best result across all six exchanges in total is total cost 95. That is a worse than the current cost of 90. Termination condition is met here. When the best available exchange produces a cost higher than the current layout, the procedure stops. So the final layout is 2314 with total cost 90. Total cost reduced from 125 to 90, a 28% improvement just in two iterations. So, let's wrap everything up. We've talked about all these, and I hope this was informative to you. Thank you for listening and thank you for your time. Have a good day.